as per the promises given by 5G. So the way I have structured the talk is at first I'll try to give a brief background on why IoT is special, given that we already have the internet, and then why the existing 3G, 4G, and all they were not. I mean, why did we not talk about IoT in the? I mean, during those evolutions, and then how 5G promises a better infrastructure for IoT, and what is exactly how MEC can fit in there with certain use cases and the possible design considerations. Okay, so right. So why do we need Internet of Things, and why do we at all talk about Internet of Things while we already have the internet? That is a fundamental question. So what is internet? Basically, I mean, it is something to boost the way civilization has progressed. I mean, you exchange data, then you share information, and from information you gather knowledge, and from knowledge you gather wisdom, and that is how the humanity has progressed. So when humanity started to rely on machines, so the idea was there that why not let machines talk to each other, and from that we started all packet switch network, and then that grew, and we had what is called internet. And what we see as internet as a mere user is basically this. I mean, you have a continent-wide spread across continents under the sea cables, optical fiber cables. Then you have got satellites on top, although that is not used that much. But you have got umpteen number of intermediary units. You may have data centers, you may have BGP routers, you may have firewalls, you have your local base station, your Wi-Fi, and so on. And of course, there are the two endpoints who are actually trying to get data from. One of them is requesting the data, and one of them is producing the data. So that is the basically the model of internet. Okay. So while we have these physical infrastructure, but you need a common language so that these infrastructures coming from umpteen number of vendors at umpteen number of layers of the technology can talk to each other. So that is why we have protocols. So which I mean, whenever we talk about HTTP or TCP, we type HTTPS:// or we type HTTP:// whatever we do. We speak about IP, any IP address. All these things are standardized so that across the globe everybody understands, or across technology, across vendor, everybody understands this. So this is basically what is internet. So there is a software which are nothing, some standardized protocols, and on top of that, of course, your end application, which is a distributed application, resides. And beneath that, there is a very complex labyrinth of wires and wireless connections, and a complex arrangement of different nodes, starting from your ISP, your mobile access point, etc. So we were happy with that, right? In 1969, we had the inception of internet. Then in 1980, we got TCP/IP and IETF as a standardization organization for the higher layers. For the upper layers, happened to produce a common language for all the communication networks, etc. Then in 1990s, we had World Wide Web as a service. We had HTTP coming in as browser, and that was the most prominent application. So World Wide Web is not just internet; it is just an application on top of the infrastructure and the protocols that I showed in earlier slides. And then from static newspaper-like pages, simple pages, then we started to evolve. Then there were active contents. Then at the start of the multimedia, with a little bit of bandwidth, we got multimedia, a little bit of streaming in 2004, 5, 6, 7, 8. We started streaming over the internet. Chats became very popular. In 2000, around 2000, mid of this first decade of this millennia, we had the social web, and then video on demand and all these things. We had YouTube coming in around 2005, 6, around that time. It started to gain popularity. Then Facebook came, or before that there was Orkut. So the concept of social media and all these things came. And then 2010 we had the smartphone. So internet have gone completely wireless last mile. Okay, so earlier there was a mix of wireless and wireline. So mostly it was wireline. The last mile connection was wireline. But since 2009, 10, this the last decade, the just what which we have just surpassed has seen phenomenal growth of wireless internet. Now the question is, so but apart from all these evolutions of these, these applications, the different manifestation of how the clients and servers can talk to each other, and but apart from that, if you look at the core, the infrastructure, the protocols were almost nearly the same for about 20, 30 years. So we spoke on, so the fundamental protocol were TCP/IP, right? And IPv4 still now is one of the most popular, or the predominant address for mechanism for addressing the entities taking part in the communication over internet, right? HTTP has been the de facto language, and it is still today. And the most important thing is, be it social media, be it a static page, even be it Amazon or a Flipkart website or any shopping website, be it email, whatever we use, the human are the producer and the consumer of the internet so far. When I say internet, I mean the information, okay, the information highway that we call internet. So human is the producer of the information content, and human is the consumer of the information content, and that is how we have been living, be whatever may be the condition. But since 2010, and thanks to the the development in sensor technology, the development in VLSI, the miniaturization of sensing devices, actuation devices, and there were several allied technological advancements in different fringes. So what we had is, people started to think is that, so we already had, even in 70s, 80s, 90s, we had something called factory automation, right? So, but within a limited sphere and with quite a bit of bulky instrumentation, and it was very difficult for us to think that whether we should go for it. I mean, whether that should be part of our daily parts and parcel of our daily life, whether it should be so as to say whether it should be part of consumer electronics. So it is not beyond industrial enterprise level work. So at that time, what we found is that, so many organizations, they came up with the concept of a smarter world, a smart universe, and all these things. So what we really meant was that you tag a suitable sensing to any device, and that device essentially becomes producer of an information, right? If that device is capable of, and this can be either a device or this can be an organ, I mean, whatever. I mean, even a human being can be producer of sensor, but unknowing. Okay, it is not that he is thinking; his brain is working for that. So anything, you attach a suitable sensor, which would sense the environment, which would help you to build an analytics or build an intelligence on top of that, so that you can have an understanding of the context of the environment, and you can have a little bit of smartness in how you deal with things, a little bit of wisdom on based on the umpteen volume of knowledge that you get. Okay, so now in 2010 we saw, or a little before that, we started to see a sea change in how you model the traffic that is traveling across this communication pipe, right? So now we see a big shift, that is, it is no longer the human-based internet, but it is the inanimate world around us who are a consumer and producer of this information highway. Now, how does that impact? That is what we need to think. See, when we think of designing an IoT system, right, we have to think of so many things. Why? Now, let me spend some time on this slide so that I can give a better understanding. So one thing is obvious, that if you are on the information highway, so like in your mailing system, you need an address. In internet also, you need an address. But how to give you that address space? That was definitely a problem, and IPv6 has come to rescue to that. But there are some other things that we need to judge. So one thing is, well, the biggest shift in traffic model that we have to understand is that earlier the traffic that we were expecting, so it was the pattern kind of followed Poisson distribution, like the telephone systems used to think of. I mean, I'm not saying that that is completely gone away. That is still there, but you still need to think a little bit more. And what was it? So now we are no longer only thinking about broadband. Now we are no longer only thinking about video on demand. What we are thinking about is there are umpteen sensors who are sensing their environment, who want to let what they have sensed and who want to put that information into the information highway, into the internet infrastructure. Now, in this case, it is not that something like a huge bandwidth will be consumed by each of the sensors. No, rather, it is small amount of data, but this small amount can, so it is just like ants attacking your food simultaneously. Hundreds and thousands of ants attacking your food simultaneously, and you consider that nightmare. Okay, so it is just like, so hundreds and billions of sensors, if they start putting their data, all are very small, all are very tiny, but they're consuming the resources at once, or in a given span of time, there's a random probability that all are coming up and using it. So the possibility is that you have the chances of melting down the internet infrastructure. So the infrastructure will completely fall. And this typical situation actually happened way back in somewhere around 1983, 84, when internet was at its infancy and TCP was not really matured enough. There was no congestion control and things, and it did happen, and that actually triggered many of the congestion control algorithms and congestion avoidance algorithms later in the standardization. So that is one thing. The other thing that we need to think about is that, imagine that all the sensors, they are all tiny, right? They are all they will be all battery powered. In many cases they will be mobile, so they are not really connected to wireline. They are not. They may not be connected to fixed energy source. They also will not have much memory. Okay, for computing. Even if it is a drone, even if it is a robot, it is a moving a moving robot somewhere. Okay, so they are not going to have a huge brain in them. I mean, huge computing capacity in them. They're not going to have huge energy, right? So how do I create my algorithm such that I'm able to honor the constraints. So IoT design is all about honoring the constraints that we have. Okay, so it is not just I give you a whole bandwidth. Okay, I give you a full bandwidth, big bandwidth, but to send on this big bandwidth, if you have too much of energy over it, okay, I'll come to these things later. That is ultimately going to make you dead, right? So the need for IoT is completely different. And then comes the question of everything is being sent and transferred to to the information highway. How do I secure them? Now, when you secure this communication, you have to appreciate one thing. The more you do communication, or the more number of bits you need to send through the communication pipe, the more number of number crunching you want to do. And if you go to any literature, you will see that there is a clear-cut warning that beyond computation, it is the communication that drains your energy the most. So 50% of the energy will be drained out in communication. So when we model the information that we want to send, or when we create the semantics of how do we communicate, when we design the underlying physical layer, the actual system that accesses the media, okay, so the all this media access control mechanism, everything, they must be as low overhead as possible. And sending of data, there has to be a judicious approach. Although when you say that you have to have a judicious approach, then you are putting computation overload, because to be judicious you have to compute. Even our brain works like that. Our brain works to identify what is judicious, what is not. So you are putting that computation load on these tiny objects, tiny sensors. Okay, so there's a trade-off that we have to do, and we have to be clever in designing. It is no longer the conventional internet that we do. So when we do security the same way, even securing will add extra amount of bits to your data, extra amount of handshaking for key exchange, etc., extra amount of storage, so key store, etc. How do we cater that? And in fact, security is still kind of an unsolved problem. That what should be the best security for IoT devices? It's still there is no one on a single answer. Okay, and the other big problem is IoT came up just like a like a big bang. Okay, so kind of there was not there, people didn't know what it is going to happen. So every enterprise, they started building their own health system, either using Bluetooth or whatever, and using any technology that is available. Or in some cases, they define their own proprietary semantics, their own proprietary technologies and all. Okay, so what happened? The market became very fragmented. So you buy the same sensor and server and the network infrastructure from the same company, you are good. It will not talk to any other company. Your sensor not talk to, so the sensor from company A will not talk to sensor from company B, or the actuator from company B. So the situation was like that. There was no standardization. The market became very fragmented, even in terms of wireless connectivity. Okay, so many people, they started using Zigbee. Somebody, they said, okay, no, let us have Bluetooth low energy. Somebody said, okay, then how do we do WAN connectivity like the internet? If my sensor has to send the data to say several hundreds of kilometers away, how do I do that? So there were several candidate technologies that came up, everybody fighting like that. So there is no consensus. Even till date, IoT is still fragmented. Although there are kind of agreements happening, many people, many efforts are dying, many efforts are evolving. So that is the complex situation for IoT. And as an engineer, as scientist, we have to appreciate IoT from this aspect, that while we have available technologies, is there anything more that is required, and what part of it can be pushed to standards, what part can be pushed to proprietary at the application level, etc. Okay, so these are some of the different configurations that we had, and cloud came in a big way for IoT. IoT management. So cloud-based infrastructure, everybody offering cloud, cloud, and cloud. So why cloud? Because you need to do software update of so many sensors. You need to do big you need to do controlling of multiple sensors. Diagnostics of multiple sensors, and you need to also store the data. Who will store the data? And you need to do analytics, because that is the purpose of getting the data. And sometimes you might also need to actuate. Okay, so a centralized system is what people all needed. Okay, and that is why this cloud, IoT cloud, and all these things came into picture, where like there are dominant cloud service providers. At the same time, there are proprietary solutions. Some people try to do some standardization on that in different domains in terms of storage, because with cloud, it came like how to store the data, so big data and everything. There was a boost up, and also at the communication level, that if you use something like a UDP kind of technology to up to your server, and then you want to put into the cloud, cloud does not trust UDP, and you still have, then there has to be a transition from your proprietary protocol to the protocol that cloud trusts at the infrastructure level. So enterprise cloud IoT was something that came up in a big way. So these are a few things that we're all, by now, we should be all familiar with. And from IETF, this became the kind of a de facto protocol stack. Like you have something like constrained application protocol, or you also use MQTT, though it is not a IETF protocol, it is from IBM, but it is open sourced, and there are some proprietary protocols. So you can have and then there's a debate like, is TLS better, is DTLS, but somebody said no, not TLS, DTLS. Then they said, okay, DTLS is heavier than TLS, then how can you fit it to constrained devices? Then there is a big gap in what should be the security layer, and several standardization, and many of them are yet to become an RFC, yet to become a standard. So the research space is still there in IoT security, because there is no single answer to that. But at the low level, it was like, okay, you have something like low PAN, okay, so it is PAN, which is a Zigbee kind of thing, so 802.11 kind of thing, and then on top of that, IPv6 was already standardized. Fine. So how this personal area network, the PAN, they are going to talk to each other? So people said, okay, we already have some existing thing. You make your smartphone a gateway, you make your some device or gateway, and you use the your existing technology as the backbone, and you do your stuff. But then that was really a quick fix for IoT. So what I want to bring in here is that people thought about IoT, even in standardization organizations, still as a personal area networking feature. Okay, it is still away from how this can mix with the wide area network, just like the internet. There has to be a technology widely accepted, which will not be vulnerable to IoT use cases, also which will support the promises of IoT use cases. So that was something that we really needed to have. Okay, so this is the kind of standardization scenario and all these things. Now, coming with this question, that what about this wide area access to IoT nodes, and what about having not so many fragmentation? Even this is even the way people are thinking about IoT. So you have a customized gateway of your own that will have a gateway application, and you have to manage your own IoT network. If you are enterprise, you have a good IT backbone, it's fine. IT people, it's fine. You are a small organization. You want to do, you get the benefit of IoT. You have to manage your IoT local network on your own, and you have to have your own gateway, and that will then in turn send the data to back to with any legacy technology. How do we get rid of all these things? How do we come to a standardized solution that will do a reconciliation of all the requirements? So if we look at the evolution of the G's, okay, so we know 1G, 2G, 3G, 4G. So we have experience, we did not have 1G in India. We have experienced 2G, and then we have experienced 3G, we have experienced 4G, and we have also seen what the different enterprises who have provided us, or the different service providers who have given us these, these Gs, how they have promised the benefits, right? So when we talk about 4G, right? So what do we get? We were given that, okay, you can download YouTube video like a flash while on move. Okay, that was the predominant use case, right? But anyway, so with these new global standards, what has been found is that IoT, with all the requirements that I have just narrated in my previous slide, while setting the context, what we found is that when we why so the question is why I am asking this question, that about wireless wide area connectivity is a problem. Why I am saying that we have 4G, right? Our mobile phones can connect over 4G, right? So why so fuss about this? The problem is IoT is not just about sending the data, but as I said, IoT is about considering or honoring the constraints. You have to be nice to these tiny objects. You have to be nice to the constraints. You have to be sympathetic to the constraints that they have. And with that only you have to design your system. That is why low pan or Zigbee was very popular, because it was a low power, low power communication technology for devices in close vicinity, okay, in a personal area network. But when we talk about broadband, we had 4G, which is, in uplink it uses SCDMA, and in downlink it uses, it uses OFDMA. Now, at the core of this, I know this better. I know this quite well, because 10 years back, I used to develop these, physical layer stack at the very bottom layer for 4G technologies and all. So OFDMA may be a little bit better than the CDMA technology, but both CDMA and OFDMA are a nightmare in terms of the power that is required and the way it has been designed, because people never thought about accommodating IoT requirements. Because when LTE started, the first time I worked on LTE standard was back in 2005. LTE was a draft standard at that point of time. So 4G was not even in the horizon. And 3GPP was unsure about the future of LTE and what could be the killer apps. So 3GPP kept on evolving 3G technology. So there we had 3.5G in terms of HSDPA, then we had HSUPA, then we had EHSPA. So all were based on CDMA technology, and I worked on these technologies back in 2008, 2009, that time. But then LTE was launched with a lot of promise, but then IoT world found itself left out. And it made things worse, because then what happened that in many cases, even myself, when I first started to connect my IoT gateways and all, I used to use a 2.5G GPRS chip for a GPRS SIM card for connecting my IoT gateway to the internet. And why I used to do that? Because GPRS was it was based on FSK and TDMA technology. TDMA as the access medium, and fundamentally it was GMSK. which is a variant of, you can say that a few grade variant of phase shifting or frequency shifting. Okay, so what happened is GPRS was much more less power hungry than the CDMA or 4G technology, but it definitely did not have that capacity. When you talk about billions of sensors connecting, it definitely does not have the capacity. So we need something that will ensure the capacity, that will ensure to put the intelligence, and that will ensure to have a very lightweight mechanism for for this narrowband communication. And also, one biggest drawback of this still 4G is that everything is driven by the operator. So the operator, so if you go to buy a plan for 4G, what do you buy? You'll buy a monolithic plan, right? Okay, so 3 GB data and this much unlimited calls and all these things. You take a say 599 rupees plan for say 56 days or whatever. So it is a monolithic plan. No matter whether you use it, whether you don't use it, you just pay. Okay. Rather, what we want is that in many of the IoT scenarios, it is not that you need the data all the time. It's just you need the bandwidth all the time. It is just when you need to send, you need bandwidth. So there has to be, there has to be a say from the endpoint also. That is the application also, and that there is no scope for 4G. So the application or the endpoint device driven resource allocation, that is also something that we need to do. Now, when 5G comes with a promise, essentially 5G is not just people. I mean, if you ask anybody, they will say, okay, 4G we had this much bandwidth, 5G we will have that much bandwidth, we will have this much, download speed and all these things. But 5G is not really all about that. 5G has come up as a promise from 3GPP and its allied organizations as a unified means to cater the different competing requirements or diverging quality of service and quality of experience requirements. Why I am saying so? On one hand, of course, we need video. We need 3D video downloaded in a flash. We need holographic video chat. Okay, so holographic video chat is, those who might not know, holographic video chat is something like when you see a 3D object of the person or a 3D avatar of that person moving around in your front. So this is like making Star Wars a reality. Okay, so that kind of bandwidth you need. Then the most exciting, one of the most exciting thing is the requirements for Industry 4.0, which is that I want to have actuation in real time with 1 millisecond latency. So my car may be in Chennai, my car may be in Bangalore, and I'm sitting here in Kolkata. Okay, so in Bengaluru, my car is there in Bengaluru, and from Kolkata, I want to drive my car in Bengaluru through that horrific traffic, whatever. Okay, and the vice versa. So can I do that? If I mean, Mr. Devi Sethi doing an operation from Bengaluru in Kolkata, is it possible? Okay, so that kind of reliable network, that kind of low latency, you see, it is a life critical matter, right? You're operating from remote. So these came up as a new requirement for 5G and new promises. So and apart from that, there were the thing that I shall have millions and millions of sensors. They should not have complain about this infrastructure, about this wide area infrastructure. They should be able to mingle with it. So on one hand, I need huge bandwidth. I need huge data rate. Latency may not be that much critical when I'm talking about video on demand or a simple video chat. But when I'm talking about somebody doing an operation from Bangalore to here in Kolkata or vice versa, I'm talking about latency. At the same time, I also need to see the object in real time, the remote object in real time. So latency, that is my control operations. So I'm rotating the objects, the needles, the knives, I'm stitching the wound, whatever I'm doing. So all my hand actions are being replicated several hundreds or thousands miles away in real time. Is that possible? Light has its own limitation. I'll come to that. But is it possible? So this is a requirement where you don't really need the bandwidth, but you need very low latency. And but when you talk about having the remote view, you're talking about bandwidth, and your latency may be a little bit delayed. Okay, you can tolerate. So this is a very contradicting situation. Now coming to machine type communication, here you may not always need latency. Sometimes you may need latency. I mean, you may need strict latency, which is for certain analytics. Sometimes you may not need, but you need to put the intelligence close. You need to have the intelligence close in such a way, placed such a way that it should appear that your tiny sensor is actually the intelligent guy, right? So there has to be something like this. So a mechanism, a infrastructural promise has to be there, and at the same time, the carrier, the access mechanism, that has to be as low power as possible. So a narrowband alternative also has to be accommodated, and 5G has that promise. Okay, through NB-IoT and all these things, where they use the same LTE spectrum and all these things, but yet they give you a band, a small band where you can do low power communication. Although I don't, there are other competing technologies, and I'm not here to comment on the comparative analysis of the competing technologies to NB-IoT. That can be a separate topic. Anyway, but 5G has this promise. So with all these things, now why we have the edge coming in here? Okay, so why we are talking about mobile edge computing as an integral part of 5G? That is something that we have to understand. So I have already narrated all the requirements of 5G, right? Or all the different spectrum of 5G. Now, if we look at the current backend internet infrastructure, even if say you are accessing something in the cloud from your mobile phone, what is the latency that you get? What is the reliability? Can you always rely on the network that will get a given guaranteed delivery? Because internet was fundamentally designed for emails. Internet was fundamentally designed for FTP. Okay, and that is the same infrastructure that is evolving. So the underlying problems are still there, and we have to live in a backward compatibility mode, but yet we have to advance to future, because we cannot let the legacy applications or legacy things just die out, right? And do at the end point, sitting at the end point, how much monitoring of the network you can do on your ISP level or wherever? Can you do? We can't. And what about melting down? So there is a cloud. Okay, cloud will definitely have its own protection. But what about multiple devices? If they try to attack at least the infrastructure will die out in between. Okay, so we have to ensure that we do not be the cause, or at least there has to be technological options that refrains such things, right? And that should be quite easy. And because internet has all these problems of congestion, and the other thing is that who ensures the resource availability? You might be accessing the cloud. Your cloud might not always give you the resource the way you want. And in fact, I have myself experienced this. I do work in robotics and these days, and I have to rely on a popular cloud service provider. I've seen that sometimes we fail to get the resource, because and you have to really pay quite high. I mean, to ensure that you always get the resource in a guaranteed form. But so there has to be some low-level control options to control at the network level. Now, so in a nutshell, the current internet, whatever it is, even if you have the 5G promises in terms of the bandwidth, because you have to, and you have to accept one thing, that 4G, 5G, and all these things, they are just the last mile, right? They are just the last mile technology. They are not going to give you, they are not going to shape up the entire internet, the pipeline I showed, right? So they are just the last mile technology up to your service provider, your ISP. So be it Airtel, Jio, Vodafone, or whatever. Okay. So I can have all these 5G and all this stuff, but what is beyond? Beyond is not changing, right? So there is a slow progress. Okay, 5G is already there. What happened to the rest of the internet? So at the last mile itself, I have to do some magic so that the rest of the internet, I can be a well-behaved citizen in the network world, right? Now there are few physical challenges. For example, light has a limitation in terms of how far it can, it can move, right? So there is a mistake in the slide. It should be 300 kilometer per millisecond, in 1 millisecond. Okay, so light can travel in one direction in 1 millisecond up to 300 kilometer. You are talking about 1 millisecond latency of your service. So there is a physics, okay, because electromagnetic wave is nothing but light wave, right? Light wave is nothing but electromagnetic wave, and that is in free space. Okay, that is your limit in physics. How do you claim that you can? And there also, I am saying that let us assume that there is no competition time taken. There is no algorithmic time taken. There is no number crunching happening. Simple light traveling, a photon traveling from one end to another. Okay. So there is a barrier in physics. So when we promise, we have to think about it. Okay. Now, if your information processing or your response units are at that far away, you can't really process things. Okay. So that is one idea for which, in order to ensure better reliability, in order to ensure better latency, in order to ensure less number of failure points, it is better that you put your content and your intelligence as close as possible, and which might also help you shape the traffic that you want to send to the internet, okay, or to the backbone. And that is where the mobile edge computing, or MEC, came up as a strong promise from its seed, right? So it sits beyond the edge and the cloud, beyond the leaf and the cloud, somewhere within the network. Now within the network, it may be in the base station, it may be at a sale aggregation point, it may be at a mobility management point, wherever it may be, there has to be an entity that is attached to the network service that you have purchased. Okay, so that is closely associated to the ISP or the network service provider. Okay, this was not the case earlier. As I said, when people talk about you have a Zigbee network, right? Then where is the gateway? You manage your own gateway. You have it on your own. You don't have, so if you buy a 4G connection from Airtel or whoever, Jio, Vodafone, whatever, you are not going to get any computation service. But in this case, network is also giving you a computation entity that you can rent, loan. Okay, right? And that is where comes the broad three-layer architecture. So I have my own network which might connect to a computing device that in turn connects me to the cloud or whatever, or depending on the application. That is why the edge is coming. Now, why in future IoT we must have MEC as a hook? I have as a design hook. Okay, design hook means that whenever you are designing an IoT system, you should always consider that I must have a an MEC in place when I consider my IoT network in a 5G ecosystem. Why we need that? Now, two things you have to understand here, and I have already narrated it. So one thing is that edge is always edge because it has to be physical proximity. Okay, so that gives you a low reaction time. Okay, and that gives you a a close to the your close to application, computation environment, and part of your application. So we are talking about a distributed system, right? So part of your application, while you are distributing, so bulk of intelligence to cloud and some of it in N, now you have a mezzanine layer. Whenever you design your algorithm, the best way is to you take it as an optimization problem. You take it as an optimization problem where the optimization rule is that I have to do computation and communication, both needs to be optimized given the constraints of my network characteristics and my own computation capacity. Given that, how much of the load should be transferred to the edge, what should go in cloud, and what I should keep with the leaf nodes. That is a typical application to application, so application dependent computation problem or optimization problem that we now need to start thinking, or people are already thinking on it, and there are papers coming out. So now having said that, let us have some ideas on like what could be the different options. Okay, so these days, even for in my case also, I started as an IoT designer, but right now I'm working on video. Okay, because day in and day out, what people are saying is that as an unobtrusive sensing, video is becoming a as a multi-purpose sensing media. Okay, video. Rather than sensing, sensing the object directly going there, because what people are saying that many analytics can run on the video feed that you are getting, and on top of that, you can have your own algorithms, own conclusions, etc. So while surveillance is, of course, one parameter, so you are getting multiple video feeds, okay, from across different parts, right? What you are going to do is you're going to send all these video to the cloud. Now, as I said, that as an optimization problem, many of these videos, and this is actually, this use case is specified at the ETE website itself. These videos can actually go to your nearest edge, and the edge coming from the operator can have the analytics module in it. You do face detection, you do whatever detection you want, you do the computation over there, and then you send it to the cloud. Only when, or only when there is a trigger, if you need to send, or you send a miniaturized version as a summary to the cloud, okay, all the time, right? So this is a typical use case for surveillance and all these things. Now there are some other use cases. I went to the 5G summit in Valencia in 2019. I think it was in June, the Global 5G Forum, Global 5G event. And in that, even people were talking about like what there was a team from Barcelona who were working like suppose there are cameras installed with no cameraman as such, and who are capturing. There is a citywide event happening. Okay, there's a citywide event happening, and cameras are installed in different strategic places. They're all sending to their nearest edges the videos. Okay, nearest edges, and these edges are part of the ISP, or suppose Vodafone is providing them the network, right? So in the core of the Vodafone network itself, there is a computing. And all these devices, rather than connecting directly to the actual broadcasting station, they're connecting to the mobile edge, okay? And there, these edge devices are putting their own intelligence so that only the interesting video feed. So it intelligently identifies which feed might be interesting enough for the viewers. And then that part is sent to the cloud, which in turn feeds the broadcasting, TV broadcasting system. So that is an interesting use case. And there are several such other use cases available. And you can think, I mean, a lot of ideas can come. Now, one thing that you have to see, what is the possible deployment option for this mobile edge platform? So on one hand, there you have got the E node B, which is the base station, and you have the core network. So if your cameras are static, if your vision sensor, and these cameras may also be thermal camera, like in a factory, you can install thermal cameras at multiple places, and only the anomaly can be sent to the cloud. At the same time, even in hospitals, I mean, you can have random thermal cameras installed to check temperature of visitors, and in case of because of the COVID-19, and only in case of an anomaly send the the data. Now, in such a scenario, either the edge can reside at the E node B itself, or somewhere in between at the RNC radio network controller level, somewhere in between the core network before it reaches internet, that is the gateway SGSN, and the immediate base station, somewhere in between it can actually reside. Okay. Now, another thing is, as I said, so you have an optimization problem, like how much of the computation that I should ideally have done at the at the end, or at the cloud, should actually be offloaded to the edge. Either it is to reduce the overhead, computation overhead at the sensor, or it is to reduce the latency that you might encounter if you send if you do the computation and respond back from the cloud, right? So for example, smart meters. Take the example of smart meters. They're all static, right? Smart meters are really not moving objects. All these smart meters, they can be connected, they can feed to the nearest edges, and the edges in turn can do the time to time configuration updates, the time to time controlling. So there can be a lot of control information being exchanged between the for diagnostics and many other parts, for regular health checkups and all these things. So if you have to send that all the way to cloud, you're overboarding the network. Rather than you put to your base network, you shift that computation to your edge computer, which is feeding the smart meters near you. So this is an example of how computation offloading or thinking or can happen, and the researchers can actually get good papers if they put this into a mathematical model, if they have optimization for optimization for certain, maybe not for all applications, in certain domains. So these can be good research objectives. Okay. Now, what about if sensors are moving? Because just like satellite, okay, if the satellite is much higher, like a geostationary satellite, so it can cover up almost half of the Earth, right? The footprint. But if the satellite comes down, it becomes medium Earth orbit, or it becomes low Earth orbit satellite. The footprint is narrower and narrower. So the same way, when you are in the cloud, you are actually catering a huge area. I mean, as much as your network is reachable. But when you are going to edge, your area of operation is shrinking, right? So the more you come down in the network stack, your availability or your footprint of the edge, if I can say so, is reducing slowly. So how do you cater the sensors on move? Now there comes this beautiful problem of edge virtualization, and there is a lot of work to be done in terms of how you place your edge efficiently. So in the earlier case, I was discussing the optimization problem between three parties, that is the cloud, the edge, or your ISP, and the end devices. But now this is an optimization problem within the ISP itself or within the network provider itself. How is that? Because now you have to think, what should be the best place to position my edge so that I can optimize on the handover communication, so that I can also optimize on the latency, because the deeper you go into the network, the more the latency is going to happen. The lowest latency you can get is from if your node is situated at the base station itself, at the E node B itself, but then you lose on your mobility, right? As soon as the sensor goes out of your cell area, your edge is just nothing. But then, if for your service all the edges are situated on E node B, what is happening? Every time the vehicle or the sensor is moving from one cell to another, there has to be a huge traffic exchange in terms of handing over not only the connectivity. It is not about connection handover, but also handing over the application context. But that will defeat the whole purpose of catering the latency requirements, that is the quality of experience and quality of service that you require. Okay, so in that case, you have to then move deeper and deeper into the network. So what should be the right position of the edge? That is a typical research problem that one can take up, and a lot of different flavors and solutions. So kind of a ready reckoner table can come up, that okay, application, if the application is classified in this category, let us have the edge, and the QoS is of this class, and the QoE is like this, traffic pattern is like this. Then let us have the edge here. Okay, so these kind of things can happen. For example, you can have in many cases, people will simply put it in the mobility management entity, the MME in the network, and between the cloud. But again, it depends on what is the latency and what is the area that you are going to cover. Okay, if it is something very location specific service that you want to give, it doesn't matter. But if it is a wide area, it will really create a problem. So having said all these things, the fundamental use case that comes up is that MEC has to act as an IoT gateway. Okay, so it is not just about computation offloading. It is not just about optimizing the traffic to the cloud. It is also about filtering the data. For example, in case of a forest fire, okay, so this, you can have the MEC acting as an IoT gateway, which filters out, which gets the sensing, all the data from all the sensors. So the sensors might be installed in multiple trees and multiple areas, in the forest. When there is a fire, everybody is starting to send the data, alert, 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 and temperature data. But then the gateway can actually do the filtering. Then also, um, also, I mean, think about the health sensors. It is not just about, I mean, only generating the alert, but it is also about shaping the data. So multiple body sensors sending in multiple form. It may happen that not all your body sensors are coming from the same vendor. They may not talk to each other. They may not have the same semantics, okay, same syntaxes. But your edge gateway can not only send the data, but they can actually packetize it. They can actually pack the data into a decent format and send a unified packet to the other one. They can also do a traffic shaping, right? So there are other important updates, other things like you can actually put the MEC to monitor the network. Okay, so for I'll come to this one later. Sorry. Yeah. So if you have the MEC server sitting somewhere, it can also sense the network. So that is what I hinted in my earlier at the very beginning, that currently in a cloud-based technology, you don't have any mechanism which can sense the network. So the virtualization of edge is one thing. The other thing is that the edge can actually decide at a more low level, ground level, on how to optimize the traffic pattern. It can actually switch the protocol in, I mean, depending on the traffic context. It can do many of the current, ABR or adaptive bitrate mechanisms that we have in current, video, video technology, including WebRTC-based video calls. It can actually do that. Okay, it can actually decide on what should be the right bit rate right now, or whether I should do an adaptive adaptive quantization of the current frame, so that I only focus on the right area which might be of interest, which might be at the field of view of the remote person, and let me put some more weightage, more quantization there. I mean, low quantization there, and let me punish highly the other areas and improve the the bit rate or the quality of experience given the current degrading network condition. So the MEC can actually have data from the ISP itself. It can get multiple sources of information from within the network, because it is sitting at the deep core at the network, or it is sitting at the edge of the network, but it is actually sniffing the network. And based on that, lot of analytics and these things can be done. So there can be multiple other use cases like crash detection in vehicle to infrastructure. Okay, so the immediate crash information can go to the edge, and from that edge, that can be distributed to all the vehicles near that region, and in turn that data gets updated to the cloud, so that the cloud can update, okay, so across locations that there was a crash at that place. So this is a typical use case, and this is also another use case for traffic optimization, right? Traffic optimization and efficient disbursement of efficient disbursement of things, information, right? And if you have an actuator, then you also need low latency control of that. So suppose within your area there is a sensor, and based on that sensing, an actuator has to do something in the factory, okay, in another factory within a vicinity. Then, I mean, you can send that actuator the sense data. The sensor can sense that, send the data to the edge, and then the actuation command can go from the edge to the actuator, rather than going all the way to the cloud. So that will ensure a low latency execution of data. And another good thing is that when the edge is residing at your operator, you have a better control in terms of asking for resources and all. And another thing is 5G has given this capability of slicing. So the thing that I said, that you have so currently the resource allocation structure is monolithic, it is completely operator driven. But when in 5G you have the idea of slicing. So slicing is that when you have something to send, you determine what is the QoS requirements, you determine what should be the channel properties, and that will in turn decide what should be the channel properties, and you create a conduit, a virtual conduit, which guarantees you this service. Now, in such a scenario, it is not the job of the tiny sensors to decide on what should be the right kind of slice for the upcoming data that it has to send immediately. That can be offloaded to MEC at the operator itself. So the MEC sitting at the operator network decides that, okay, this application, this sensor is going to send this data. What should be the right slice, network slice for it, and it helps allocate that slice. And the biggest benefit is that it helps computing that slice. It helps to compute that slice. Okay, so this is the slice that the sensor will require. So this computation can be offloaded to edge, and there is a standardization opportunity, and people are actually working. I have seen this in many European organizations, especially around Greece. I've seen many organizations who are actually trying to standardize the application level interface, that given that you have an application and there is an operator who has given you an edge, so how the application, what should be the interface, standardized interface using which the application should tell the edge that this is what I need, and in turn the edge will tell the operator that this is how you should arrange the slice, see if you can do it. So to kind of conclude, let us talk a little bit about the deployment scenarios. So as I said, edge can be deployed at the node B, it can be deployed at the radio network controller, it can be deployed at the cell aggregation point, or at a multi radio access technology aggregation point. For example, maybe one section of the enterprise is working on Wi-Fi 6, one section of the enterprise is working on true 5G network, one section of the enterprise might be so there is a personal 4G is something that is also getting popularity. So it may happen that at the enterprise level there is an aggregation point, and the edge actually sits at the aggregation point, so that it can reconcile the requirements coming from the different sections of data coming from working in different radio access technology. At the same time, it may go indoor, it may go outdoor, depending on what should be the coverage scenario. So in a stadium kind of environment, I mean, you can have an outdoor MEC there. But what are the factors that could drive the decision? So there cannot be a single answer. That is why whenever I was talking about research opportunities and all, or optimization opportunities, I'm always saying that I mean, it is good if you can classify the applications, put the applications, put the different kind of applications into different kind of buckets, and then you create a ready reckoner, okay, based on imperial analysis, based on I mean, benchmarking or whatever, based on theoretical computation, theoretical modeling, you can do that. Okay, depending on how much scalability you need, depending on whether you have a physical constraint. So physical constraint might be like your E node B is located on a rooftop, where I mean, you find it very difficult to install an edge device over there. Okay, it may happen. Or even if you can install an edge, it may not be powerful enough, right? So how you are going to what are the scenarios that you are going to deploy in? What are the physical infrastructural hindrances that you might get? Performance criteria is another thing. So these are all multiple factors that one person. So every time there has to be an optimization because there are so many options in front. So all these are actually becoming constraints based on which you should optimize constraint factors. And then what is the scale of network information exposure? And now that is very critical because in many cases what is happening, the ISPs are not the computing vendors, okay, computing power vendors. So computing power vendors are who are essentially traditional cloud players, like Azure is there, Amazon is there, Alibaba is there in China, and many other partners. They are not the ones who are ISPs, right? Who provide the network service. Network service is provided by Vodafone and Three and Verizon and many others. So when this thing has to happen, there has to be actually a handshaking between the cloud service provider who will chunk out a little bit, will come with a piece of computing environment, and that has to be installed into the mobile edge, into the mobile network. And so now, so there has to be a third party handshake, right? Now there's a problem. The problem is that if the network service coming from another party, right? The network service provider will always have a look at the application, that the data that is flowing, the traffic pattern that is going through. Now you are a computing vendor. You are putting your stuff over there. You are computing stuff over there. Now, what is the scale of trust between these two organizations? So how much network data do you want to expose to the computing vendor? That is one typical question that one must ask, because the deeper you go into the network, the deeper your computation device goes into the network, the more overview of the network data you are getting, right? So if these two are coming from two different vendors, so there has to be a kind of an agreement and kind of a trade-off, like how much deep you can go and which up to which layer you can actually have access to network information. So these are some of the deployment scenarios and some questions. So what are the key challenges, not really related to IoT or anything, but in general, not only related to IoT, but in general for MEC? So what is the, when you have to make a decision, so you have to make the right decision at the right time for computation offloading. And if there are researchers who have been working on distributed computing, they can take this up as a special case of distributed computing and then a computation optimization. But at the same time, I'll put a word of caution. I've seen that many distributed computing people, they don't even consider the communication link in question. Okay, so even if you talk to anybody who are working on AI or anything or neural networks, where a distributed computing units are involved, what I've seen that they have given a single weight to the single weight one to each of the link, but that is not the practical case. So when you do a distributed computing, you have to keep in mind that without the communication infrastructure in place, your distribution is not going to work. And your distribution should not happen such a way that you do a computationally optimized distribution, which is not communication optimized. Then your system is going to melt out, because you have to remember, to distribute you need to communicate, and the more you communicate, the more overhead you put on your devices, for all the devices. So task offloading is a very complex complex problem that should take care of the underlying link, the current capacity, and the capacity of the capacity of the requester, and the capacity of all the requested nodes. Okay, so how you do optimization of that, that is something that you must take care. Otherwise, what I've seen that in many cases people have designed distributed solution, they have done it, but in reality, when they have deployed it, it did not work. They have just shrugged it off, saying that it's not my problem because communication is not my domain, but it is your domain because in a sense that in if you are you know how to cook, you should also know that what is the right utensil that you need to use, because there are certain metals which do not go with, for example, you can't put sour stuff in copper metal, right? So you have to have that much of knowledge. You may not be the one who is preparing the utensil, who is preparing the infrastructure, but you should be at least aware that what should be the right infrastructural decisions, or what should be my approach given the kind of infrastructure I might be I might have. So this is something that without that things will not actually work in practice. Mobility management is definitely one problem that I've said, and of course, if you are working at the edge, then the problem is definitely how to efficiently allocate computing resources with minimal latency. Okay, so it should not happen that I'm waiting with the data. I've requested for a service as an end application, and when I have gone to the edge, the decision making process for how much computing resource to allocate to this guy is so huge that ultimately my end-to-end latency, my end-to-end quality of experience suffers. It should not happen that way. So these are some of the challenges and the trends that we are going to watch out in 2021 and beyond. We're going to see more machine learning and AI on edge devices, and more partnership between cloud service providers and edge providers coming together along with the network service providers. And already Amazon has partnered with many network service providers with at different parts of the world. We still don't have 5G in India, so we'll see that happening once the spectrums are available to different operators. I think only one operator has it now. So what we have seen in, like in London, Amazon has partnered with Vodafone, right? So they will partner with different and same way the other Azure and all, they have also partnered with different networks to provide, because as I said that this is an opportunity for network, because now the problem is that computing service providers, they want to be part of the communication, and the communication service providers, they want to be part of computing. So now they two have to marry. Okay, so that is what is going to happen, and more of 5G adoption is going to happen, because in 5G they have allowed the the ISM band has been already the private given in 5G, and there is a big boost for it. Even the device-to-device network category has come up with a promise for long-range ISM band communication. So private deployment, limited deployment, also the dense cell concept is giving you low range, low range high frequency communication with 5G with small cells. So private deployment is something that is going to happen with the MEC. And so what would happen, like just like I have right now from a broadband service provider, I'm taking a broadband the same way. I might see that I've got a private 5G network around my home, etc., or around my enterprise, but I have only a small base station located somewhere which is actually connecting directly to the 5G backbone. So right now, the broadband service provider, the normal Wi-Fi broadband service providers, they don't talk to any 5G ISP or anybody. They actually go through the normal gateway, the countrywide gateways and all this communication. They don't really talk to any ISPs, mobile ISPs. Okay, so these are a few things that are going to happen. And with that, I'd like to conclude. If you have any question, you can ask. Thank you.
Sir, there is a question on the chat box.
Can you? I'm not able to open the chat box for some reason.
Okay,
I don't know why.
I'll read it for you.
Yeah, sure.
Okay, for a researcher, what are the problems in MC?
So yeah, as I said, the thing is, what you need is basically you can either do my device optimization. You can either do optimization in terms of computation offloading. You can in terms of in terms of how you allocate resources, and there are like how you can take part in in slicing, right? In helping you in slicing, and what are the requirements of slicing? That is something you can do, and and at the core network, many people what they are doing is they're actually designing on different analytics. Okay, so 5G analytics is a big thing that is coming up. Okay, so what you can do is you can actually work on you fix on a use case, and then you think that how I can do some analytics on top of that, such that uh, uh, an edge can be involved. Because I tell you one thing, and I have experienced it. One of the problem that even the edge providers they are getting is that um, when they're trying to sell edge, it is good theoretically we talk about so many use cases and so many possibilities, but in real life, in many cases they're finding it very difficult to sell edge as a product. So enterprises have convinced that why they should disrupt, whatever little bit disruption that might happen, why they should invest on an edge. Okay, so that can come up from a nice theoretical analysis of what is the data, or what is the of that for a given application, how it may be an existing application, but how you can distribute this application such a way an edge, incorporating an edge is going to give you benefit. Most of the in many cases, the researchers who are working on edge, basically they are working mostly assuming that I have a computation requirement, and how do I allocate my resources? Okay, do I do efficient allocation of resources? But there can be another approach to it also, which is given a problem, how do I bring out better efficiency of the performance, and so that I can show that there is a if you do a clear segregation of responsibilities between edge, cloud, and this thing, or you can offshoot some part and put a satellite in the form of edge. How does it benefit? So this can also be an interesting problem that can help enterprises who are trying to sell edge as a service. So these are some broad areas that you can do, and there can be many more. You study the literature and you will get. It is still a kind of a not really green field or not really gray field, but I'd say in between. Yeah. So if there are any more questions, I can answer.
Okay, I don't know. From the Department of Electronics and Telecommunication. Your participation, thorough investigation into the topic what you have put in, and put have in this department. sir.
Thank you. Thank you for inviting. Thanks a lot.
Okay. The chat box, please find time, fill up the feedback. And keep this meeting open for another 30 minutes. By the time we should be able to complete the feedback. For tomorrow's session, as you know, both of these sessions are hands-on, right? The session tomorrow is Cloud Intelligence to Edge Device with Azure IoT Edge. It is a session conducted by the director, EakTech. Hands-on session. When you attend the session tomorrow, it is better you be prepared with your laptop or desktops. And so does the second session also. This course, Quantity OS who better hands-on. Mr. Sound thread will be taking action on it. Please be prepared. And probably by this time, you will also have received the procedure to download Quantity OS and install on your systems. And if you can do it by the time of the second session tomorrow, it would be nice of an interactive session. You can or the Quantity OS as well as Kuja. Thank you. We are going to close the session now. If any, you can put it in the chat. We'll try to reply to it.